This video will cover the squeeze theorem. So this is one of the many theorems that you will be responsible for knowing for this class, and this is the first one. So let A be an element of the real numbers, and let F, G, and H be real valued functions such that f of x is less than or equal to g of x is less than or equal to h of x for all x in an open interval containing A but not necessarily at A itself. If the following happens, where the limit of f of x as x approaches A ends up being equal to the limit of h of x as x approaches A, so these equal the same value, then, well, what do you think would happen? So let's say we have these three functions, and based on this inequality, we see that g is between f and h. So along this interval, we're able to determine that the limit of f and the limit of h were the same thing. So I think it would be natural to assume, and you would be right, that given this condition, where f and h reveal the same limit and g is squeezed between them, then the limit of g as x approaches A should be the same as the limit for f and h. That is the squeeze theorem. Now, let's look at an example and why it's important to know how to use this. Let's say g of x is equal to, so we'll just look at an example, x squared times sine of 1 over x. And you're asked to evaluate the limit of g of x as x approaches 0. Now, when you look at this, I can't picture that graph necessarily very well in my head, and upon direct substitution, which is what I would use for something algebraically, this x squared piece would go to 0, but what about this 1 over x? I'm going to get 1 divided by 0, which is undefined. And am I properly evaluating a limit where I have to take sine of some undefined value? Likelihood of that is no, but I don't know also how to manipulate this algebraically, so we got to analyze this in a different way. And what I can do is when I look at this function, what I recall from trig graphs is this value out in front. When I multiply a trig function like a sine or a cosine by some value in front, that dictates the amplitude of the function. So if you recall, if we have some form of a sinusoidal function where we have a sine x or a cosine x, this a, so this oscillates between plus or minus a, right? We learned that in pre-calc. Now, it doesn't necessarily have to be constrained to a constant like a. It could be a function itself. So when I see x squared sine of 1 over x, I recognize that this sine of 1 over x should oscillate between plus or minus x squared. So again, we learned in pre-calc how to identify amplitude, but amplitude is not constrained to just a constant number. We can actually oscillate between functions. And because I recognize that, I can make the determination that this x squared sine of 1 over x is stuck between x squared and negative x squared. And that sounds a lot like the squeeze theorem we just defined. And it's easy for me to compute a limit of x squared and negative x squared. And if those happen to be the same, then I can make the determination on the original limit question. So we can say it would be natural to choose f of x to equal negative x squared and h of x to equal positive x squared. So our g of x is what we're trying to evaluate. And remember, f of x and h of x, based on our definition above, are the two functions that g of x would be squeezed between. Now, if I evaluate the limit of f of x as x approaches 0, well, that's just going to be the limit of negative x squared as x approaches 0, which through direct substitution reveals it's just 0. And then the limit of h of x as x approaches 0 is equal to the limit of positive x squared as x approaches 0. I don't need these either. And through direct substitution, I get 0. So because these are the same, by the squeeze theorem, we can say that the limit of g of x as x approaches 0 is equal to 0 as well. Because again, we established that negative x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to positive x squared. And based on our definition above, we can just say, well, this is our f of x in that definition, this is our g of x, and this is our h of x. And just to get a visual, we can jump over to Desmos to check out what these graphs actually look like. So what I have graphed here is a picture of x squared times sine of 1 over x. Now, you might not have this available, but just so you can see how it gets stuck between plus or minus x squared as we expected. If I turn on these two graphs, as we zoom in, you can see that as we approach 0, you can see that this pink graph here, which represents the function g of x, is getting squeezed between our h of x, which is positive x squared, and our negative x squared, which is our f of x. So if we can compute the limits for f and h, we expect the limit for g to be the same as long as f and h reveal the same limit at that point. So that is the squeeze theorem.